Imagine the shock. Centuries of scientific dogma shattered by a few simple but devastating experiments, each one, in its own way, delivering a fatal blow to the idea the Earth is hurtling through space at unimaginable speeds. Instead, these experiments delivered a message that echoed through the halls of science. The Earth might be stationary. But rather than confront this possibility, the scientific establishment found itself scrambling for a get-out clause. And what came next would forever change the course of physics. In our last episode, we explored the crucial experiments that proved a stationary Earth. Those findings, taken together, presented a crisis for accepted science, a direct challenge to the heliocentric model. Experiments involving light travel through the medium that makes up space, the ether, were consistently delivering null results when measuring Earth's translationary movement around the Sun. What was to be done? The first attempt to explain away this crisis came in the form of the Fitzgerald-Lorentz contraction hypothesis. In 1892, just 5 years after the Michelson-Morley experiment, Irish physicist George Fitzgerald proposed that objects physically contract in the direction of their motion through the ether, shrinking just enough to cancel out the expected ether wind. This mind-bending idea was expanded by Dutch physicist Hendrik Lorentz, who developed a more precise mathematical framework for this so-called length contraction. The theory suggested that if the arms of the Michelson-Morley interferometer physically shortened as they moved through the ether, the light would arrive back at the same time, erasing the expected interference pattern. This was a radical move, to say the least, introducing the idea that physical objects themselves could change size depending on their motion without any observable physical cause. As Sir Arthur Eddington put it, the Michelson-Morley experiment has thus failed to detect our motion through the ether, because the effect looked for, the delay of one of the light waves, is exactly compensated by an automatic contraction of the matter forming the apparatus. The Lorentz transformation seems to have been a desperate ad hoc attempt to preserve the moving Earth narrative despite the contradictory data. But this contraction effect, crucially, has never been directly observed or experimentally verified. It existed purely as a mathematical convenience to save the Copernican paradigm. James A. Coleman offered the following insight in his book Relativity for the Layman. The explanation which had the most appeal in accounting for the negative result of the Michelson-Morley experiment was one that was literally dreamt up for the purpose. It is the so-called Fitzgerald-Lorentz contraction. In 1893, Fitzgerald suggested that all objects contracted in the direction of their motion through the ether. He reasoned that if ordinary objects flattened out upon impact with other objects, a rubber ball hitting a wall or a ripe tomato dropped on the floor, for example, then why would it not be possible for objects that move through the ether to have the force of the ether push them in or contract them. This would adequately explain the results of the Michelson-Morley experiment. The arm of the interferometer moving against the ether would be shortened so that even though the light wave travelling in that particular arm might be slowed down by the ether wind, this would be compensated for by having its path shortened. Objections to the Fitzgerald-Lorentz contraction hypothesis were rampant, as was to be expected, not only because there was no evidence to prove that such an effect took place, but particularly because Fitzgerald could not explain why objects would contract due to motion through the ether. The contraction hypothesis was originally advanced only as a possible explanation for Michelson and Morley's results, providing such an effect existed. Then, too, the theory said that all materials travelling with the same velocity with respect to the ether would contract the same fractional amount. Since iron is much heavier and stronger than wood, for example, one would expect a greater contraction for wood than for iron, but this too went unanswered. The science fiction nature and circular reasoning of this incredibly shrinking matter hypothesis was highlighted by Dennis Sciama in his book The Unity of the Universe. He said, "No one would take this theory seriously, of course. One reason for this, no doubt, would be the obviously ad hoc and indeed ludicrous appearance of the theory. But the fundamental reason for objecting the theory is that the demons cannot be observed except through the very phenomenon they were invented to explain. The introduction of the demon thus adds nothing to what we already know." To all intents and purposes, creative theoretical science and math magic had come to the rescue, but failed to convince many. The idea of apparatus being squeezed just the right amount to explain the embarrassing scientific enigmas of these important turn-of-the-century physical experiments was simply too much to bear for thinking individuals. Then, in 1905, a young patent clerk named Albert Einstein took this idea even further. In his paper on special relativity, Einstein proposed that not only lengths, but time itself could stretch and contract depending on an observer's frame of reference. This new theoretical science not only insisted on shrinking equipment, but also required slower clocks to account for the results. The hypothesis grew more and more ridiculous. Crucially, Einstein discarded the concept of the ether entirely, declaring that light travelled at a constant speed regardless the motion of the source or the observer. This removed the need for ether effects, effectively sweeping the very inconvenient Michelson-Morley null results under the rug. Einstein's approach came at a huge cost. It denied the existence of an absolute frame of reference, declaring that all motion is relative and that there is no universal backdrop against which to measure movement. Without the ether, Einstein had to explain the mechanics of length and time contraction by other means than the Lorentz transformation with the ether. As William Maguy pointed out in 1912, the principle of relativity accounts for the negative result of the experiment of Michelson and Morley, but without an ether, how do we account for the interference phenomenon which made that experiment possible? Einstein's answer was to simply say that motion in and of itself caused the phenomenon, with the concept of ether being superfluous. And all of this simply because nobody could accept the plain result of the experiments, that the Earth did not move. So circular reasoning simply had to be employed to save appearances. The syllogism for Einstein and his generation can be summed up as follows. Major premise: we can't detect any movement of the Earth. Minor premise: we simply know that the Earth moves. Conclusion: we must accept a creative and exotic new physics called relativity. This was much more palatable than the alternative of accepting a non-moving Earth and the absolute revs frame that accompanies it. The special theory was hugely controversial at the time. Unlike Lorentz, there was simply nothing physical to cause the contraction. It was space-time contracting by itself, with the speed of light taking up the mantle of the new absolute constant. Not everyone agreed with it, but most agreed that the contraction of the apparatus must be real. Otherwise, they needed to accept a static Earth. However, even Einstein himself was not entirely comfortable with the implications of his theory. As he developed his general theory of relativity, published in 1915, he reintroduced a concept strikingly similar to the ether of old, though he mostly avoided the term. This space-time fabric, a flexible, dynamic entity that could bend and ripple under the influence of mass and energy, brought back the need for a medium through which gravitational waves could travel. Essentially, a modern form of the ether. In a 1920 lecture at the University of Leiden, Einstein himself admitted as much, saying, "According to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. According to the general theory of relativity, space without an ether is unthinkable." So, despite the early rejection of the ether, it had quietly crept back into mainstream physics, hidden behind the complex mathematics of curved space-time. Ludwig Kostrow, in his book Einstein and the Ether, documents Einstein's own words regarding his remarkable U-turn on the ether. In 1905, I was of the opinion that it was no longer allowed to speak about the ether in physics. This opinion, however, was too radical, as we will see later when we discuss the general theory of relativity. It does remain allowed, as always, to introduce a medium filling all space and to assume that the electromagnetic fields, and matter as well, are its states. Once again, empty space appears as endowed with physical properties, i.e., no longer is physically empty, as seemed to be the case according to special relativity. One can thus say that the ether is resurrected in the general theory of relativity, since in the new theory, metric facts can no longer be separated from true physical facts. The concepts of space and ether merge together. Today, a century later, the idea of the ether is stronger than ever. Quantum mechanics, the Casimir effect, zero-point energy, and the discovery of the Higgs field have all pointed to a rich, energetic medium filling what was once thought to be empty space. Physicists now speak of the quantum vacuum as a seething sea of Planck particles and an all-pervasive energy field, a far cry from the sterile void imagined in the wake of special relativity's rise. Robert B. Laughlin, the 1993 Nobel laureate in physics, gives us the following remarkable statement in his book regarding the return of the ether. It is ironic that Einstein's most creative work, the general theory of relativity, should boil down to the conceptualizing space as a medium when his original premise was that no such medium existed. Einstein utterly rejected the idea of ether, and inferred from its non-existence that the equations of electromagnetism had to be relative. But this same thought process led in the end to the very ether he had first rejected, albeit one with some special properties that ordinary elastic matter does not have. The word ether has extremely negative connotations in theoretical physics because of its past association with opposition to relativity. This is unfortunate because, stripped of these connotations, it rather nicely captures the way most physicists actually think about the vacuum. In the early days of relativity, the conviction that light must be waves of something ran so strong that Einstein was widely dismissed. Even when Michelson and Morley demonstrated that the Earth's orbital motion through the ether could not be detected, opponents argued that the Earth must be dragging an envelope of ether along with it, because relativity was lunacy and could not possibly be right. Relativity actually says nothing about the existence or non-existence of matter pervading the universe, only that such matter must have relativistic symmetry. It turns out that such matter exists. About the time relativity was becoming accepted, studies of radioactivity began showing that the empty vacuum of space had spectroscopic structure similar to that of ordinary quantum solids and fluids. Subsequent studies with large particle accelerators have now led us to understand that space is more like a piece of window glass than ideal Newtonian emptiness. It is filled with stuff that is normally transparent but can be made visible by hitting it sufficiently hard to knock out a part. The modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic ether. But we do not call it this because it is taboo. In other words, the very concept that was abandoned to save the heliocentric model has re-emerged as a cornerstone of modern physics, once again challenging the foundational assumptions of our understanding of the universe. Kostrow, in his book Einstein and the Ether, sums up the return of the ether model. Modern science has its roots in ancient Greek philosophy. This philosophy, as we know, used the word ether to designate the particular kind of matter that filled the universe. This term was used throughout the history of philosophy and science, and it was also current at the beginning of this century. A resumption of its use at the dawn of this century is now a fact, since, according to the general theory of relativity and other modern branches of physics, the space and time of the universe do not constitute a vacuum, but a structured material plenum characterized by different physical quantities. The historical and traditional word ether is the most appropriate to express these features of the universe. S. Sanders and H. R. Brown say in the book The Philosophy of the Vacuum of 1991, "Today the vacuum is recognized as a rich physical medium. A general theory of the vacuum is thus a theory of everything, a universal theory. It would be appropriate to call the vacuum ether once again." Frank Wilczek, professor of physics at MIT and Nobel Prize winner of 2004, said, "Prior to the 20th century, physics tried to explain how nature works. Over the 20th century, and especially in the last half, we got much more ambitious. Now we're uncovering what nature is. The foundation is an entity I call the grid. The grid fills space and is full of spontaneous activity. In some ways it resembles the old idea of ether, but the grid is highly evolved ether, ether on steroids if you like, with many new features. We have some wonderful ideas waiting to be tested. There are good reasons to think that the universe is a multi-layered, multicoloured superconductor, that all four known forces can be brought together in a unified theory. That seemingly hopeless different kinds of matter are just different aspects of one all-embracing stuff." I anticipate that the next few years will be a new golden age in fundamental physics. Robert Moon, Professor Emeritus in Physics at University of Chicago, uncovers the quandary that mainstream science is in. He said, "According to accepted theory, free space is a vacuum. If this is so, how can it exhibit impedance? But it does." The answer, of course, is that there is no such thing as a vacuum, and what we call free space has structure. The impedance equals 376 plus ohms. The Michelson-Morley experiment had to be dismissed to uphold a moving Earth, and the scapegoat was the impossibility of the ether. Einstein's special theory achieved this, but then he completely backtracked on the fundamentals with the general theory. So the pertinent question to be asked is, why is it not then reasonable to return to Michelson-Morley with ether intact and accept its results that prove the Earth stands still? The results of Michelson, Sagnac et al. Continue to be quietly ignored by mainstream science up to modern times. It's important to reiterate that all these interferometer experimental results were not in fact null results as claimed. In all instances, some fringe shift was detected, and it so happens the small positive result is precisely explained by a slow but consistent ether wind, as would be expected by a diurnal rotation of the universe around the Earth in the geocentric view, or vice versa in the heliocentric view. This is consistently ignored by relativists. As noted physicist Dayton Miller, who did over 100,000 trials on this very subject with the most sophisticated equipment to date, noted in a letter of 1930, "It is true that nearly all the writers at the present time interpret their experiments as giving a definite null effect, and most of them assume that it is final. The truth of the matter is the experiment never gave a null effect. My present determinations are exactly in agreement with the 1887 results of Michelson and Morley. This fact has been widely announced, especially in England, but the theory of relativity seems to be so acceptable to many persons that they overlook the apparent discrepancy." Ironically, one of the core doctrines of relativity is that any celestial body can be the centre of the universe, lending support to geocentrism rather than disproving it. Essentially, the best relativists can now hope for in the battle for the centre of the universe is a draw. What happens when we apply this new understanding of space to the grandest scales of the cosmos? What if the very fabric of the universe itself is telling us that Earth is not just stationary, but at the very centre of it all? In our next episode, we'll dive into the astonishing results of modern satellite missions like WMAP, the Planck probe, and the Sloan Digital Sky Survey, which have revealed a startling truth about our place in the cosmos, one that threatens to shatter the very foundation of the Copernican principle.